We're so very excited for another episode here. I'm Haley.
And I'm Jonny.
There you go. Are you with me here? And this is Dr. Joe Pesce, and he is here to talk to us about science today. And this is Jonny, Haley,
Jonny, Haleigh.
Dr. Joe, Day of Fun.
Day of Fun.
And we're so super excited to have you here. So I
Thank
know
you.
that you have kind of a broad swath of things that you are able to speak on in terms of science. Astronomy is your area of expertise. So if you can give just a little introduction to yourself and your background.
Yeah, sure. Great. Thanks for having me.
Mhm.
I'm
Yeah.
looking forward to
Pleasure.
having fun. So I'm a astrophysicist, and my research area is supermassive black holes in galaxies and how they affect the galaxies that surround them and vice versa.
That's
Okay.
definitely one of my favorite subjects. So we will definitely have to get into that. And I know that so recently you had visited the ALMA Observatory in Santiago, Chile. I know that you said. So can you talk a little bit about that facility and the equipment that they have and what is the work that they sort of focus on?
Yeah, sure. So ALMA is an acronym for the Atacama Large Millimeter Submillimeter Array, ALMA. And it's a radio telescope, radio observatory in northern Chile, high in the Atacama Desert at about 16,500 feet altitude, 5,100 meters. And it needs to be there because the light that ALMA observes is absorbed by water vapor in our atmosphere. And so you need to be in a very dry place so those little photons of light aren't absorbed by water vapor. And it's very dry there. And ALMA is making fantastic observations of mostly the cold universe. So gas that forms stars and planets, gas that's within galaxies, gas that's around black holes and in the very early universe. And it's making fantastic observations. It's a tremendous observatory. It's one of the most complicated scientific instruments on Earth, and it's one of the most sought after instruments. So astronomers who use it apply for time, and if they have a project that's of interest, then they're granted observing time. And the oversubscription is very large. So for every hour of observing time, there's maybe 6 or 7 hours of requested observing time. So this is it doesn't sound like a good thing, but it's a good thing. It means that astronomers are really interested
It's
in using
in high
this
demand, right? Everybody wants to be
Yes,
there.
exactly.
Yeah, for
Very
sure.
cool. Very cool. So I know John had another question he wanted to ask.
Yeah. I was gonna say, like, as far as like things that you study in the sciences that you study, what are some things that still puzzle you? Like, because a lot of people would say like black holes or like maybe even parallel universe theory, you know what I mean? There's different avenues you can go. So what still puzzles you as a scientist?
So I can say that actually, almost everything is a puzzle, right? So
Yeah.
astronomy, we know a lot about the universe, and we know a lot about the universe through our astronomical observations. But like any science, nothing is concrete and
Mm-hmm.
definitive. We don't know. We think we know things, but there's more to learn. So almost everything in astronomy is actually kind of puzzling, right? You look at it and you think, the universe is doing this fantastic stuff,
Mm-hmm.
making stars, and stars work and planets form, and we're finding that planets are probably around every star and every
Yeah.
every uh, so it's all just amazing, and we learn new things every day, and we realize that the stuff we thought we knew, we don't fully know. Having said that, so that's kind of a flip answer. But it's
Yeah.
true.
Oh no,
But
it is true, and that's why you keep doing science, so you can keep
Yep.
searching and finding the next new truth and the next information that we didn't know existed, and if you didn't investigate it, you wouldn't know.
no, that's right. And people think that when science is settled, as lots of things in astronomy, that's a definitive answer. And that's not how science works, right? There's always an observation that's going to come tomorrow that might throw that in complete disarray, and then we have to start over from scratch.
Yep.
One of these, or a couple of these areas that I'm finding really interesting and perplexing at the moment is observations by ALMA that we just talked about, and by the Webb Space Telescope, which
Yep.
is a new and shiny instrument that's out there in space and is actually quite complementary with ALMA. They're observing similar things in different parts of the electromagnetic spectrum, so we're getting a bigger picture of the objects that both observatories observe. But
Okay.
what we are seeing from these two observatories, but not only from other ones as well, as we gain better instruments on existing observatories, we're seeing objects in the very early universe that aren't behaving as we expected them to. So what do I mean?
Okay.
Yeah, when you say very early universe, right? Because light travels, what we're seeing is essentially the past, right? When we're observing
Yes.
what's happening out there.
Yes.
So that's such an interesting
Mhm.
way to sort of visualize it. So yeah, do talk more about that.
Yeah, so astronomy, as you point out, is a time machine, right? Everything we observe astronomically, even the most nearby object like the moon, right,
Mhm.
we're observing it in the past because light takes time to travel to us. So the very early universe, right? We have this model that Big Bang formed the
Mhm.
universe. And so when I say very early universe, I'm talking 200, 300 million years after the Big Bang, maybe up to a billion years after the Big Bang.
Mhm.
And as our instruments become better and better, we're able to see further into the past, that is closer to the Big Bang event. And what
Okay.
we're observing with Webb and ALMA primarily, but again, not only, are big galaxies that are bigger than they should be, kind of in the 300 to 500 million year range after the Big Bang. And we're seeing very large supermassive black holes at about the same time that are so big, we don't know how they got that big. And in fact, according to the 3 or 4 ways that we think black holes, big black holes can become that large, there's not enough time for them, in that 2, 3, 4, 500 million years after the Big Bang to have become that large. And so we're seeing these big structures there at a time when it seems physically impossible that they could have become so large. And so,
That's
this is telling
really
us that,
interesting. I
Yeah,
mean,
that's
because
interesting.
you have to measure it kind of based on the observations we have of other black holes that are, I don't know, I guess you would say nearer or younger is could maybe the right way to say it. So, I mean, it's interesting, sort of like the further you get out, then the further away you get, does I guess maybe time seem to operate differently then? Is there something, or what's the theory there, or are there theories there on, okay, well, if it should not be that big in that amount of time, does time operate differently where they are, and or how is time affected in the distance between us and what we're observing? That's kind of breaks my brain to think about it a little bit.
Yeah, right.
so that's an interesting way of looking at it, frankly, and it's one that I haven't thought about. I think perhaps though that time is maybe not changing, although I'll have to go away and think about this because maybe that is our solution.
But
But I think
it's interesting, but like the I think of like I know I don't, again, I'm not a scientist myself, but like I am a kind of a science nerd. I like these concepts, and I watch a lot
sure.
of Nova and things like that.
Mhm.
And I think time dilation is one of the things I was thinking about in like quantum physics. Is there something there that if you extrapolate that out into like a much larger scale, could it also have that kind of similar effect that would be happening in that distance where time is affected based on, you know, the fact that light is the only thing, right, that is at that constant speed.
Mm-hmm.
So I don't know, it's
in
interesting.
vacuum, yes. So
In a vacuum.
That is an interesting perspective. It in science, we like to use the concept of Occam's razor, which is the simplest explanation is probably the more likely one, or at least that's the one we go with until something proves otherwise. So if it were a time variation effect, that would have very complicated knock-on aspects for basically everything. So I think rather the solution is going to be that our understanding of how galaxies form and how supermassive black holes form is flawed in some way.
Okay.
We think we know pretty well how that works, but as we started off saying, we don't know everything, and we can certainly be wrong. And I think that the simpler explanation is that our understanding of black hole formation and galaxy formation is just not complete. And so these new observations they're certainly showing us that that's almost certainly the case, right? Because we have these things that are unexpected and we can't explain them. So it could be that something funky is happening in the early universe in a way that we hadn't anticipated. Maybe it's time. I think more likely it's that we just don't have a complete understanding. We don't know as well as we think we do. What's going on with black holes and galaxies. But again, that's the nature of science, and new observations come up and they show us something completely unexpected, and now we have to try to figure out what's going on. And so it's really quite exciting, I think.
It is really exciting. And for me, like, we've talked about a little bit before, like I do write science fiction also. So, sort of incorporating the more speculative elements of science and what could these things be is really exciting for me. So, in the realm of puzzles of the universe, like I do love the questions about like black holes and like what's on the other side, sort of, so to speak, of a black hole, right? And like if you could throw something in there that would give information back to us, like where is it going? Where does it lead to? And so if you could talk a little bit about that, and another topic like for me that is really fascinating is like dark matter. And it kind of goes along with black holes in my mind in, again, the science fiction realm so far, that if could there be like dark matter or black holes could be part of like parallel universes that, I don't know if maybe wormholes are kind of those sort of things that people speculate about, but that fascinates me, the idea that there might be something just right here, right next to us, so to speak, that is just it is a different frequency or something that we don't understand how to interact with based on our sensory observation, right? That it's there, we just don't vibrate at the same rate or something, and so we don't interact with it.
Yes, that certainly could be the case. Some of these things we have to think very carefully, though, because they are science fiction, and so we're using our imagination to think about these things, and we can certainly postulate, come up with some sort of idea of something, but unless we can test it, of course, then it's not scientific, and it is in that realm of science fiction. So along those lines, starting kind of backwards from what you were saying, because you mentioned something that's very near to us that we're not necessarily able to detect. In some theories of the universe, we have multiple universes that are in a certain dimension are only millimeters away from us, right? So these universes are stacked next to each other in a particular dimension, and they're literally only millimeters away in that dimension. And so that could certainly be the case. Again, I'm not aware of any way that we can test that at the moment, and so that has to remain in the realm of science fiction.
But it's such a fun theory, right? Like it's
so
fun to play with.
For
Yeah,
sure.
absolutely, in all cases. But one of the things that I find intriguing is that we have the force of gravity, right? And the force of gravity is one of four fundamental forces. The other forces are operating mostly at the nuclear level and subatomic particles and at the in the centers of atoms in their nucleus. And it's what keeps particles sticking together, and it's what keeps protons attracting electrons and whatnot. So these other forces, they are very strong in a relative sense compared to gravity. And
Okay.
gravity, not only is gravity different in that it operates at a much larger scale than these other three forces that are acting on subatomic particles, gravity operates on a much larger scale, but it's also tremendously weaker than all these other forces. And it's not completely understood why that's the case. Some speculation, or
Yeah.
science fiction speculation at the moment, is that the graviton, which is a particle of gravity, just like a photon is a particle of electromagnetic radiation, the graviton, for whatever reason, can travel between these parallel universes. And we know in our universe that gravity, the force of gravity, drops off over distance, and so the further you are from a mass, the weaker the gravitational attraction is. And so if the graviton is traveling through these parallel universes without us really realizing that, because we can't tell that that's happening, then as it's traveling through the parallel universes, it's traveling much further than we would have expected if it's just coming through our universe. And
That's
so then the force,
interesting.
and so that might be why the force of gravity is so weak, because it's traveled much larger distance than just traveling through our universe. It's going through multiple universes.
That's really
Again,
interesting. That is a super fun theory. I like that.
yes.
Yeah.
So maybe one day we'll be able to test that. We can't today, so that remains in the realm of science fiction rather than science fact. But it is something interesting to think about.
It is really interesting to think about. So, if you could talk a little bit too, though, about like black holes. I again, from things that I've watched on Nova, one of the things that they talked about was that, and I don't know if I maybe understood it very well, but like the outside of a black hole sort of contains the information of light or things that have gone into it in some way. I don't know if I was understanding that, but if you could talk a little bit about that and how that works, or how we currently understand how it works.
Sure. So that the black hole is a region of space where matter and gravity fundamentally has uh, gravity has basically crushed matter out of existence, and that creates what we call the singularity. So very energetic events create the singularity, such as very large stars, much bigger than our sun, exploding violently in what we call a supernova. And that explosion can crush the central region of the star before it exploded down into nothing. And so it creates this thing called singularity. What do I mean nothing? I mean spatially, there's zero dimension.
That's hard to visualize. That's
in fact, it's impossible to visualize,
yeah,
right?
because
And even more so, the former core of the star, the mass, has not disappeared. It's still there because you can't get rid of mass, right? So that in the laws of nature, we have the conservation of matter and energy. We can go between matter and energy, the famous E equals mc squared equation, right? Einstein's famous equation. You can change, you have matter on one side, mass on one side, and energy on the other side. You can go back and forth. There's an equality. So you can create matter out of energy, and you can create energy out of matter, but you can't get rid of
right.
either. So the central region of this massive star that exploded and collapsed now has zero radius, but all of the mass is retained. So that means that the density is infinitely large. and it makes a very extreme gravitational anomaly, which is what we call the black hole. Okay, I'll come back to that in a second.
I was gonna
Now,
say this fascinates me so much, and I do try to visualize it in my mind, but it's again like, how do you visualize nothing? You can't.
Yes. Well, so you can't visualize nothing, but you can visualize that intense gravitational field, right? If we had a sheet of rubber and you put a bowling ball in there, right, you see the deformation.
Mm-hmm.
If I now have something that I've crushed out of existence and have a mass that I've crushed out of existence and have zero radius, that deformation is a deep, infinitely small hole in the sheet of rubber, right?
Mm-hmm.
So that's what we call the singularity. Outside of that, we have something that does have a dimension that's called the event horizon.
Mm-hmm.
And the event horizon is basically the last orbit. If something is orbiting the singularity, it's the last orbit outside of which something can escape. So me as an astronaut floating
Mm-hmm.
around, right? If I'm outside of the event horizon, I can hope to escape off into more distant space, and within which the event horizon, I will fall into presumably the singularity. So the event horizon is that region, again, within which nothing can escape that falls through it, not even light. So astronauts, spaceships, pieces of dust, planets, right? Photons of light, if they fall through the event horizon, they're never coming out again.
Okay.
Presumably, and I say presumably because we don't know what happens inside of the event horizon, everything falls into the singularity. We don't know what happens inside of the event horizon because nothing can escape.
So,
and in particular, information can't escape. So I can't send a spacecraft that's transmitting, a message as it's falling in. As it's falling in, it's transmitting that message, but once it falls through the event horizon,
it's gone.
It's gone, and the message doesn't escape. So we don't know what happens within the event horizon.
Okay.
So I don't know if it goes together or not. I guess in my mind, I'm thinking of like dark matter, and they talk about dark matter is, the only thing you really know about it is that it has mass and does not interact with light. So is there anything then comparative between the two? Dark matter doesn't interact with light, and then the singularity beyond the event horizon of a black hole also doesn't interact with light. So, it is dark matter, again, science fiction speculation, right? Is dark matter sort of the other side of the black hole, right? Like not the event horizon that we can see, but whatever it is on inside the singularity, and that's what dark matter is. And then on the outside of that are all those other infinite galaxies and universes, or what have you, that are stacked on top of each other. That's the thing that fascinates me. Obviously, again, how do you test that? I have no idea.
So before we get to dark matter, let me make one point about the black hole and why we can't understand what happens. We can't understand what happens at the singularity because it has a zero dimension. Its radius is zero.
Okay.
And if you think about many of the laws of nature, and certainly the laws of nature that would apply here, we have an equation, and that equation has a radius in the denominator of the equation. But now we have a radius that equals zero. And as we all know, you can't divide by zero, right? So those laws of nature then are no longer valid at the singularity. And so that's basically why we can't understand what's going on. Because the laws that describe everything are invalid. It doesn't mean that there aren't other laws or other equations that describe that. It's just that we don't know what those are.
Right.
Okay. So there's mass there. There's an extreme gravity field there that's operating on a very small dimension. But there's probably nothing unusual, right? I mean, it's unlikely, although not impossible, that the black hole, the singularity, is a portal into another universe or something.
The
Maybe it is.
wormholes
Again,
that people talk about, right?
Mhm.
exactly. It could be. I just said we don't know, and so that's
Because
certainly
how
a
do you,
possibility.
yeah, how do you test it if everything that
Well,
goes in there goes away?
yes,
There's
Mhm.
no
yes.
way to
So
get that
so
information back.
that's right. So you can't test it physically. I mean, we can think about it theoretically and create models
Mhm.
and whatever simulations and that sort of thing using different laws of nature that we might come up with that might work in that environment. But we haven't yet, and so that will probably happen in the future. Um, Dark matter is probably a completely different beast.
Okay.
And
Okay.
as you point out, it has dark matter, as far as we can tell, has mass, and interacts very weakly, if at all, although probably it does interact with light in or electromagnetic radiation in some way, but just very, very weakly. And so it's almost impossible to detect in any other ways. Now, interestingly, when dark matter was first detected, and it was basically detected by measuring the masses of galaxies like our own. And it was seen that, as you move further and further out from the edge of where the stars are in galaxy, there's gas
Mhm.
clouds that go beyond the edge. Uh, the mass doesn't fall off as you would expect, right? So think about a CD, right, or
Hmm.
a vinyl record, if we go
Yep.
back even
Yeah.
further in time, and you have a disc, right, and that disc has mass in it, and
Mhm.
once you go past the edge of the disc and you go further and further out, if you're measuring the mass that's within, where you're measuring the ring that you're measuring, uh, the mass stays constant, and then as you get bigger and bigger, it's going to start dropping off. And so
Okay.
similarly, we thought that galaxies should behave this way, but they don't. They show that their mass continues to at least be flat, if not increase, as you go beyond the visible edge, which means that
Okay.
there's something there that we can't see.
Hmm.
There's mass
Okay.
there that we can't see. And then going beyond that, when you realize that there's probably this stuff that we call dark matter, um, it also explains how galaxies remain stable the way that we observe them. Uh,
Mhm.
it, our
Almost like they're
models for
kind
how
of
galaxies
sitting in something, sort of.
they're sitting in something that's kind of keeping them stable in the way that we observe them. If some of our models indicate that, if we didn't have dark matter, galaxies would blow apart. The stars, orbiting in the galaxy would fly apart, and they don't. And
Hmm.
so this is another indication that there's something unseen
Hmm.
electromagnetically, but detected gravitationally, and this is dark matter.
Okay.
So when dark matter was detected, you immediately think, well, what can it be? And black holes were thought to be a candidate because
Okay.
we can't see black holes, right? Black
Hmm.
holes are by definition, you can't see them electromagnetically
Hmm.
directly. You can see them indirectly, but not directly. And so it was thought, well, maybe there are huge numbers of black holes out there and they are forming, we can't see them electromagnetically, but they're forming this so-called dark matter.
Hmm.
Well, that's certainly possible, and there are certainly huge numbers of black holes out there. Not only the big ones that are in the centers of galaxies that I study, but the ones that are caused by these exploding stars, the supernovae, that are much smaller. There's probably hundreds of millions of them within our galaxy.
Hmm.
But number one, that's not enough to form the dark matter. And number two, um, if they were forming dark matter at the numbers that they would need to be, we would be able to detect them in other ways.
Oh,
Okay.
okay.
And we don't. And so there are lots of black holes out there. It's just that there's not enough of them to form
To account for
dark
the
matter.
dark matter, because it's like
So
80% of the
Okay.
universe, they say, is dark matter, right? So
Yes.
that's interesting. So
80% of the matter of the universe.
of the matter of the universe is dark matter, right? That's
Because there's
That's
another
wild.
thing that's even freakier called dark energy that we can come to later if you want.
well, no, I'd love to talk about. Tell me about dark energy.
Yeah.
This is new to me. This is fascinating. So because then I start to wonder, okay, if this dark matter is sort of holding things in place in certain ways, then is there something about the way that dark matter behaves, again, when you're looking into, like you say, the distant universe or the older universe? Is there does it continue to, I don't know, become more dense, I guess, is that the way to say it? I don't know, but does the dark matter operate differently the further out that you go, away from where you are, to be able to observe outward, right? That might account for why things are not in a bigger size than what you think that they should be for the time that we presume they've had to develop. I don't know.
Yeah, it certainly could be, right? And dark matter, the operative word there is matter. It behaves exactly gravitationally just like matter that we're familiar with, the stuff
mm-hmm.
that's around us that we can see. And so it tracks, or rather I should say that because matter that we can see is a small fraction of the matter in the universe. So the matter that we can see tracks dark matter nicely. They seem to go hand in hand. Dark matter accumulates around galaxies just where matter is, and it's found in clusters of galaxies where the galaxies are. And so they seem to be intimately connected. And again, that's kind of what you would expect if you have stuff that is being operated on by gravity.
Mm-hmm.
You are correct that as we look further into the early universe, and it's a younger universe, by the way. So when we look at more distant objects, we're looking at a universe that's younger than it is today, because we're looking in the past, right? We're going
right,
back.
right.
And so certainly the universe was smaller as we go further in the past, because the universe is expanding, and so now
right.
it's what it is. If when we go back in time, it's getting smaller and smaller. So yes, the density of matter and dark matter is increasing. The universal density of matter and dark matter is increasing. And so absolutely, it could be that dark matter is playing an important role in those early objects in a way that we hadn't anticipated. That could certainly be the case.
That's really interesting. I do love that. That's the mysteries of the universe really are endless, aren't they?
Well, and here's the mystery, and Jonny asked this when we first started. What's something that's that's really maybe disturbing, right? And a disturbing thing here is that we think we know what dark matter is. That is that it's some type of subatomic particle.
Okay.
That hasn't been detected yet.
Mm-hmm.
And the hasn't been detected yet is becoming problematic, because we thought with experiments in particle accelerators like the Large Hadron Collider, say, in Europe, we thought that we would be detecting these particles, these theoretical particles that we believe make up dark matter, and we have yet to detect them. And that's becoming problematic. Because if we don't, then there's something wrong with our models. And
that's interesting.
Something wrong, the something that could be wrong with our models could be catastrophically wrong. And yet the models, we think we understand them very well, and they explain a whole range of things, not only in fundamental physics and particle physics, but also larger scale in cosmology and astrophysics. And so if there's a fundamental problem with, again, our models and our understanding of how nature works, that's really quite disturbing, kind of scary, in fact. Although again, right? So on one hand,
I think of it as being a little bit exciting, though, that maybe there is something very, very, very cool that we just haven't stumbled onto yet, and maybe it's not that our models are wrong; they're just incomplete, right?
There's always a thrill of the unknown.
Exactly. Yes. And so scary in the sense that, everything we know might be wrong, but exciting, in that, hey, we're going to learn something new, right?
Yeah.
Yeah.
So can you tell us what is like, because you did say dark energy. So now I have to
Yeah.
know a little bit
let's say
more
that.
before John goes, because I know he's got
Yeah,
another
go ahead.
question, but like the idea of dark energy, what is this? What?
Yeah. So, and that's why I specified when you said 80%,
Yeah.
matter, because now, again, remember, matter, energy, right? So there's a matter and an energy budget in the universe. And when you look at that, this so-called dark energy is in fact 95% of what's out there in the universe. And
Okay.
5% is matter. Of that 5%, 80 or 90% is dark matter, and the rest, the minuscule fraction that remains, is stuff that we can see, stars,
That we can
galaxies,
observe.
planets, us,
Yeah.
and humans, right? So the matter that we observe in the universe is just a minuscule, it's like the scum on the surface of a bathtub, right? Maybe even less than that.
Yeah.
So what is dark energy? Well, let me tell you how it was detected, first of all.
Okay.
Okay.
The short answer of what dark energy is we don't know. But okay, so
Sure. But
here's the detection. So we have these things that are called, in astronomy, that are called standard candles.
okay.
Because light, uh, uh, as you move away from a light source, the intensity of the light drops, right? And so if I have a flashlight or a candle that's 1 foot in front of me, it's going to be brighter than if it's 2 feet in front of me, and so forth, if I'm measuring it with an instrument. And so we can, and it drops off in a known way. The brightness drops off in a known way. So this is interesting because we can use that fact to measure distance if we know how bright the candle is.
Okay.
Right? So if I have the candle in my laboratory and I measure exactly how bright it is, if I can transport that candle to the moon and I measure it on Earth, it's going to be fainter than in my laboratory, but I can compare my measured faintness with how bright it truly is. And there's a distance term in there. So I can calculate what the distance is to great accuracy.
Okay.
So we have these things in astronomy that we call standard candles. And there are all sorts of different astronomical objects. The ones I'm going to talk about now are exploding stars, supernovae. So there's a class of supernovae that we think, through observation, we've determined that when these stars explode, they get brighter, and then they peak out in brightness, and then they drop down and become faint again. That peak brightness is the same for every similar type of supernova.
Okay.
And as far as we can tell, it's the same everywhere in the universe that we can observe that. So that's great because we observe, one night we go out with our telescope and we observe one of these supernovae in a distant galaxy. It's a standard candle. We know how bright it is fundamentally. We measure how bright it is on the sky. We can determine the distance. Okay. So a project 20 years ago now was looking at these supernovae about 1 billion light years away, so 1 billion years in the past.
Okay.
And they were observing dozens and dozens of them. And when they analyzed the data, they realized that something was wrong because they were fainter than they should have been.
Okay.
And so the first question is, we've made a mistake. Right?
Okay.
So the team that's studying this looked at every possible mistake they could have made, some sort of error that they might have made. Was it an error in the instrument? Was there, some problem with the data analysis? Were their computers injecting some sort of error? And they couldn't find any issues. And then not only that, but independent groups started making these observations with completely different instruments, and they observed the same thing, that they're fainter than they should be.
Okay.
So then you start to question, well, is there something going on 1 billion years ago, right? Maybe there's maybe there's material between us and those supernovae that are causing the light to become fainter, right? If there's dust clouds in between us that we don't know
Right.
about, and the
Like
light is
something
traveling through the
obstructing the
dust.
light.
Exactly.
Yeah, for sure.
Exactly. So all of these measures for about 10 years, several teams were looking at this and trying to find out what went wrong, because that's the most obvious thing. We made a mistake, right? We're just human after all.
Yeah.
And they realized that, there was no mistake. And so how can something be fainter than it's expected to be? What might you do to make an object fainter than it should be?
Besides putting something in front of it to obstruct the
Yeah.
light,
Yeah.
I can't. If
Yeah,
there's
yeah,
nothing in
besides
the
all sorts of
way,
errors. Yeah, if there's nothing in the way, there's no errors in the instruments. What if I
Yep.
move it a little bit further away than I expected it to be? It's going to be fainter, right?
Yeah.
oh,
The
so
further
it's
away
further
lights are.
away than you think it is.
Okay.
Yes. So we're measuring objects at 1 billion light years away, but they're not 1 billion light years away. They're slightly further, and that's what's making them fainter. So how can that be? And the only way that can be is if the universe is expanding, and
Mhm.
we know that, and that's
Mhm.
pretty settled science. Although again, details are still missing.
Right.
But
Yeah.
the universe is expanding. So if an object at a certain distance is further than we expect it to be, that means that the expansion is not uniform. It's
Right.
increasing in this case. And as it turns out that coincidentally, with the study, about 1 billion years ago, the universe started to accelerate in expansion and expand faster than it had been.
Okay.
Is there any kind of, I don't know if how you would measure it, but is there an event horizon sort of situation of where that, or is it a gradual situation where it like gradually is expanding, that there's an acceleration? Like, because I'm thinking in terms of, if you're again the disc or the vinyl record sort of imagery,
Sure.
right? The further out that you go, it's faster the further out the expansion.
Well, that's certainly the case, right? The faster the further away you are from any point, that expansion is moving more rapidly. That's certainly the case, but it's linear as you go back. I mean, if you took that that rubber sheet that I was using to demonstrate the gravity, and it's 2 dimensions, and we all get on a side, and there's 100 of us, and we're pulling it, stretching it uniformly. In the middle, the stretching is going to be a small amount, but on the edges, the stretching is going to be a large amount.
Okay, right.
For a given amount of time. So that means that the edges of that rubber sheet are moving faster than the middle, and the universe operates this way as well. To answer your question, we don't. So the teams are looking at this now to see what that acceleration or what the expansion is doing over time, and that's still work in progress. But it does appear that it was uniform up to about 1 billion years ago, more or less, and then it started to accelerate. And the only way that can happen is if energy is being thrown into the universe.
Okay.
And that energy is what we call dark energy, right? Because you can't, you need to, I mean, you're telling the universe, you need to provide energy to do that. And that energy is what we call dark energy.
And we don't know where that comes from or that's right. I mean,
it's like, not clear exactly what it is. It's probably happening at the quantum mechanical level.
Okay, right. So
now,
very difficult to detect when it's that far away.
Yeah.
Yes, that's correct. And but I will add that very, very shortly after the Big Bang, and perhaps we can discuss this in another time, since our time is rapidly.
It's all really super fascinating. So happy to talk for as long as you're willing to talk with us about it. Because this is really great stuff.
Yeah, it's fascinating.
Mm-hmm.
So very early on, we have what's called the inflationary period. And what happens is the universe, and I'm talking 10 to the minus 35th of a second, so a minuscule fraction of a second after the Big Bang. The universe is the size of an atom, and within a minuscule fraction of a second, it inflates to the size of a grapefruit. 10 to the 50, so 1 followed by 50 zeros, orders of 10 to the 50 factor. It inflates from the size of an atom to the size of a grapefruit, and then expands uniformly thereafter, up until a billion years ago, and then it starts to accelerate again. So what appears, it wasn't clear, and it still isn't, what caused that inflationary period, very early on, but it's probably the same thing. It's probably this dark energy that's, and why is this happening? It appears to be a ratio between energy and matter. And when the ratio between energy and matter in the universe changes, and energy, kind of dominates, then it causes inflation. And that happened early on, and it happened, a billion years ago. It might happen again. There may be some structure in there in between that we haven't detected yet, but this appears to be the case. What exactly is doing this is still unknown, and that's an open area of modern cosmology, the subfield of astrophysics that looks at the universe as a whole. Now, you could say, well, that's kind of, you mentioned this inflationary period, and that's kind of bogus. Why would you just throw that in there? And in fact, we say in common parlance, we say the Big Bang theory. It's actually the inflationary model, because the inflationary model is the one that took over from the original Big Bang.
Right.
And it described the
because
period.
the question I have is, okay, well, if the Big Bang is like, the universe was an atom and then like to the grapefruit, it's like, okay, well, what was the universe sitting in before it did that? Right?
So in fact,
what?
Yes.
Because there's not just nothing and then all the things, right? Or is there? Do we know?
There probably is, right? And
well,
so
they say before the Big Bang, the universe fit into the size of a pen tip, basically, or like yeah.
Well, in fact, the at the Big Bang event, the universe was probably a singularity.
Okay.
So something that had zero size, but all the mass. And so when I said that inflation started 10 to the minus 35th of a second after the Big Bang, and the universe at that point was the size of an atom, it had grown from basically nothing into something that was the size of an atomic nucleus, I should say, not an atom. So what I mean, this is the problem with language, right? We say
it's
the universe
very limited, isn't it?
Right.
Exactly. And there was probably nothing there. There's certainly, we are not expanding into anything. The universe expanding is what there is, right? And this is mind-boggling.
It is, because you think, the universe is infinite, space is infinite, and infinity is obviously something our minds are not built to understand or contain, really. Right. But if it's expanding, it doesn't make sense, right? It's counterintuitive. If you blow up a water balloon and it starts taking up more space, there's something around it that it's taking, even if it's air or in the atmosphere, right? So we're just a bubble, and outside of it's like non-existence. Like, how do you
there's nothing outside. Yeah, that's the problem. So exactly to your point, we're blowing up a balloon, and that's blowing up into the atmosphere, but that's not what happens in the universe. Which, for that analogy to work, and this is difficult, but you need to imagine yourself as a two-dimensional creature on the surface of the balloon, right? So think about that.
Right.
You're a two-dimensional creature.
You're a stick figure that some kid drew on the balloon.
On the balloon, right? There's no up and down, right? There's left and right and forward and backwards, because those are the two dimensions. And now the balloon is expanding. And what's happening to the rubber of the balloon? It's stretching, right? And so your universe is expanding, but it's not expanding into anything because there's nothing in two dimensions, there's nothing to expand into. It's only us sitting out here outside of that saying, oh, well, we're three dimensions, and so the third dimension. So if you're truly two-dimensional on the surface of the balloon, you're not expanding into anything. Your space, the fabric of the balloon,
Right.
the fabric of space is expanding and creating a larger and larger universe for you.
Right.
And so in a similar way, we're three-dimensional, of course, and so it's different than the two-dimensional creature, but it's the same thing. The universe is expanding and creating a larger and larger universe, but it's not going into anything.
It's so fascinating for me to think about. It really is. And you know, because that's the other thing I always wonder is like, okay, well, you say like the Big Bang and you think of it expanding, like, okay, well, where's the middle? How do you determine where the
middle?
Well, you know, so so you can't.
Well, preferred, yes.
Everything that you measure is measured just based on where your device is, whatever you're measuring from.
Exactly.
So if you put it in space, you know, it has to measure, you know, you can get that measurement from out there, but otherwise from where we are, we have to measure from where we are. And
exactly.
you know, so it's
That's
also
right.
fascinating. Like I said, it kind of breaks my brain a little bit when I start thinking about it. It's big ideas, you know.
Yeah.
But in a good way though, right?
It is in a very
for
good
sure. I
way,
love this
very
stuff.
exciting way.
Yeah, I
So
was gonna say there was like this is probably a two-part question. A, with this occupation, how do you get any sleep at night? Because I mean, with my brain, it's like how do you turn that circus off that's going on 24 hours a day?
You know, I mean, sometimes there are problems that we're working on, and yeah, that keeps you up. Or more likely, you know, you're working all day on something and you can't figure it out, and in the middle of the night you wake up and you say, you know, I figured it out. So
there it is.
There are moments like that, but I do have to say that, you know, it's mind-boggling, certainly.
Yeah.
You know, the universe, right?
Absolutely.
I do in when I teach at university, you know, my first lecture, I talk about scales, and because distances in the universe are incomprehensible, and so you have to scale things, and even if you scale them in a way that, you know, we can understand as humans, you still rapidly exceed that. So it's truly is mind-boggling and mind-numbing, and you know, we come to, because we look at things through like a lens of mathematics, and you know, we throw out huge numbers that are meaningless in and of themselves, but we understand what that means. And so there's a little bit of the romantic nature of astronomy that, you know, we kind of lose because we become embedded in that, and without thinking really hard, if you did, you would realize that it's mind-boggling, and you know, but it's not. And so from that perspective, I guess I can say I sleep well at night, but you know, when I sit back,
sometimes you just have to let it go and just let it be what it is.
Exactly.
Well,
but when you reflect on it, though, it's just amazing, right?
Yeah.
And just, you know, you look at these images from any astronomical instrument, but certainly, you know, the modern one, the the new Webb images or whatever, and it's just phenomenal. And then you sit down and you think, okay, well, you know, that's 10 light years across, and you know, there's whatever mass of dust in there, and you know, it's meaningless when you say the number, but it's just awe-inspiring.
It is that there's so much out there, and then there's so much that, you know, that you don't know about what's out there, and it continues to make more stuff that you don't know about. The more that you can like measure it and validate things, and the more that you can put on sort of, I guess, the map, as so to say, you know, it's expanding exponentially. So by the time you get this much understood, there's that much more out there that it's, you know, been cooking up and making that you got to figure out now.
Yeah. For sure.
and how insignificant we are, right? In
for
our
sure.
little corner of the universe.
Right.
But also how
And
amazing though, because with all the things that are out there and all the things that we can see and that continuously are being created, you know, here we are on our little blue pearl in our little piece of the
yeah.
cosmos, you know, floating around and watching TikTok and YouTube and, you know, and running our little everyday lives. I mean, it's kind of amazing to think that humans developed, even right, of all the things that are out there, that we're able to observe things that are that far out and have come to that space. It is really amazing to look at humanity where we are.
Yes, indeed. And you know, you think about what makes us up, right? So these fundamental elements, mostly hydrogen, right?
Mm-hmm.
And oxygen and a smattering of other things. And you know, those were all well, the hydrogen comes from the Big Bang, but everything else is from the interior of massive stars. And someone said, I can't remember who it was, that, you know, we humans are what we are the universe understanding itself.
Yeah.
I think the paraphrasing of that, which, and it's true, right? So we're components of the universe, and yet we're put together in a way that we can ponder and understand what's going on.
And that,
you know,
that really
probably
is
other things.
That's the incredible thing, right? If we're all made up of the same atoms and the same quantum stuff, and we are self-aware and have now had that ability to be self-reflective and sentient, you know, what else out there has had the time to do that but looks nothing like us, you know? And I mean, aliens is one way to think of it, but then you have to wonder, like, does that look like an organic life form like us, or is there a dust cloud out there that has just been around so long that it's somehow self-aware? And again, that goes into that science fiction realm, but it's certainly a fun idea to play with.
Yeah, well, that's the thing. It's like everyone thinks aliens are, you know, these tall, you know, human-like things. A little puddle of bacteria could be considered an alien life form. You know what I mean? That's the thing. It's such a there's such a gray area there. I think that it's like it can go either way. You know,
there's so much out there. Like there has to be something, right?
I think so. Yes.
You would think so. Yeah.
Which is a whole other conversation that could take up a whole other hour, I'm sure.
Oh, absolutely. Yeah.
I was gonna say my second part to that question, quick.
Sure.
So I had two people in my life that kind of got me into science as far as looking up and just more or less being okay with questions not being answered instead of everything having an answer. Neil deGrasse Tyson was one of them. And then my science teacher, Bill Molaskey, he was an educator first, and I think that was important for the time because I was a punk kid and I needed direction more than anything. But they always taught me, like, they always said you can't look at space exploration without looking at colonization. So the question is, what viable food source could sustain a population on Mars if we were to go to Mars?
Yeah, we like the colonization theories that are out there, or I don't know, what would you call those?
I'm just looking at, like, what options would we have that would sustain us as a population and give us nutrients to basically live. You know what I mean? Like, that we wouldn't just wither off.
John wants to know if we're still going to have burgers and fries if we all go to Mars.
Maybe, right? So potatoes. I mean, you know, that was, of course, in The Martian.
The Martian,
yeah.
They say that potatoes are, you know, are a good crop to use on Mars. So I'll start by saying that this is a little bit out of my realm of expertise, but you know, I mean, so we have explicit nutritional needs, and those are going to have to be met, right? And I was always intrigued by. So I'm a Star Trek. I'm a Trekkie.
For sure.
At heart, more than anything else. Although I love it all, you know, and much of science fiction, you have biscuit-like things that you eat, and they have 100% of nutrients and whatnot. And I suspect that at some level we may be able to do that. Although one can question the highly processed nature of that sort of thing. Though I would have thought until a colony or until explorers are self-sufficient in some way, that is being able to grow things, and I think that's going to be necessary at some point. You're going to have that sort of freeze-dried stuff that we see on at the International Space Station, for example,
right.
or some sort of nutrient cubes or something, just because transporting stuff is so difficult.
Yeah.
And I don't know how you get around that. I don't know how you get around that easily. I mean, that's the biggest issue, of course, of interplanetary or even interstellar travel is mass. You're moving, you have to move a lot of mass, and so you want to minimize that.
So like your proteins and stuff like that would more than likely come from supplements like pills and powders and stuff like that, and then you would supplement carbohydrates with potatoes.
I would, I think so, but but that's not very healthy. I mean, even
No.
Right.
No,
because we have those sorts of supplements now, right? And it's not an ideal situation. So maybe you're okay with a non-ideal situation for 10 years or whatever, however long that you need, just to get you to bootstrap over. But I think we'll really need to be able to do something different, and I fully expect that stuff can be done in the lab, right? So
for sure.
maybe we don't have to grow potatoes or spinach or whatever, but we can grow potato cells in a petri dish.
I mean, there is some like the other element to that, I think, would be psychological, right? That like as humans, food is something that is necessary, but that certainly in our culture, at least, or there's other things attached to it, right? We have holidays and big meals together for a reason, right? There's that I don't know if you would want to maybe say more creative element about food and variety and the diversity of food that we have access to that would not having that would probably be a detriment to, I guess, mental health. It's obviously not perfect for your body situation generally, but then like, what are the mental effects of that?
But don't you think that could be trained out?
Well, I mean, that depends, right? I'm certainly not looking for that training because I'm a big fan of the food here on Earth.
No, of course.
But yeah, you would have to be willing to train yourself into that's not why you're there.
Well, I think
go ahead, John.
Oh, I was gonna say, I think the biggest thing with the food thing, like in outer space or like in Mars, would be like you would have to sacrifice indulgence for necessity. You know what I mean? You would have this much to eat. You could, chocolate cake, thing in the past, probably. You know what I mean?
Yeah.
You would eat what you needed, not what you wanted, basically.
Right. Or certainly what you had, right?
For sure.
But I was thinking like an intergenerational, starship or 100 years on Mars. Slowly with the generations, you might have to engineer this in that you're no longer doing the food-based cultural things that humans on Earth have done.
So the culture of the colony would be very different. You might be getting your energy a different way, and so you would have to. The creativity element of food, the way that we see it, wouldn't necessarily be something that would exist there. That's just not. So what would they find to replace it would be the other interesting exploration, I suppose, right? If you're not spending that time cooking and watching the fun cooking shows on Food Network and what have you, right? Then what are you, doing with your time? Kind of thing.
Sure. Yeah. Well, I think that so I come back to Star Trek, right? And Star Trek is in a post-monetary civilization where you don't have to work, right? Because everything is provided and you don't need money or whatever. And so what do you do with your free time? And it's the same sort of question, right? So I'm no longer watching cooking shows, but I'm doing something else.
Right. What's the new thing you create?
Yeah. And the first generation or two is probably, that's going to be problematic and people are just going to have to make do. But, I can imagine a time that, someone finds our diary and they think back, grandma and grandpa, they mentioned something about chocolate cake, and what is this thing?
What is
I think
this
it's something
chocolate?
to eat, but
Yeah.
What is this chocolate you speak of? What?
Mhm.
we haven't been
I
able
love
to
it.
figure out what that word means or
Yeah,
whatever.
again,
Yeah.
language is limited, and if you can't like find some chemical breakdown of what it is to be able to try to recreate it in their lab, don't know what that is.
For
So
sure.
fascinating. I love
Right.
it. Well, we do again want to be respectful of your time, but just so appreciate you coming to talk to us about this stuff. I
Yeah,
like
it was
we
a great conversation.
do honestly hours of this. So, Dr.
Yeah.
Joe, we'd love for you to be our regular, like, this is the new science news story. Please explain this to us. We're fascinated but confused.
Right.
That would be great.
Just tell us
yeah,
I was gonna say, just tell us the stuff that's gonna scare us. That's all that we want to hear.
That's yeah.
Well, that's the net. So we've passed Halloween, but yeah, there's a lot of scary stuff out there that we can talk about. Yes, but I'd love to come back and thank you. I had a great time too.
Absolutely.
Yes, thank you so much. Well, I have been Haleigh.
I've been Jonny.
And this has been Dr. Joe. And this has been Jonny, Haleigh,
Haleigh,
Dr. Joe, Day of Fun. Thank you so much for listening, y'all. Do please check out all the links that we'll put in the description. You can find more information about the observatories. We'll share out Dr. Joe's information. You can go find him, and you check us out on Patreon, patreon.com/JonnyHaleighDOF. And thank you so much, everyone, for listening. This has been great. I've had so much fun.
Yeah, me too.
Me too. Thanks.
Thank you.